Hello, Craig here with Practical 2 of Geos 1110's Module 1, the Solid Earth. And we're looking at rocks today, even more rocks. So this practical is what rocks and minerals actually are and what they tell us about the ancient environment. So in this practical, we're looking on a short tour of the rock garden, which is outside the main earth science offices and teaching labs. And we're also going to look at a rock collection in a lab as well, try and get a feel for what these different rocks are, what sort of environments they formed in, where they might be found on the Earth today. So, normally in nice weather we take you outside and we walk around the rock garden, and we're going to be trying to do this remotely and virtually. However, I've got some really good shots of a lot of the rock garden that I think you'll probably get a better view of the rocks than we would normally get standing around outside anyway. So, as you notice, same deal as the earlier Prac on Prac 1, there's a number of questions in here that you guys should think about filling out as we go. Now, some of these I think you can probably self-research. The answers for these sorts of things are in the textbook, so with a little bit of reading you can cover it. And as always, the practical answers will be made available at some point after the quizzes are all done. So, the rocks we were going to look at in the rock garden, if you scroll through, we have a map here, and here's the main geoscience offices, here's the teaching labs just here, and the rock garden we're looking at is actually at the front of biology to start with. And the rocks we're going to talk about start with this one here is rock 1, this one here is rock 2, rock 3 is here, rock 4 is over here, and rock 5. And then we take a tour back up Wally's Walk to near the teaching labs to this rock garden, the Earth Science Garden, where we look at a particular rock just there, and then via a couple little detours we'll end up looking at another rock which is hidden in the vines down here. And they constitute our 7 rocks that we're going to be talking about in our walk through the rock garden. Now, we have a couple of other things here. We talk a little bit about classification of rocks. Now, one thing we don't expect you to get out of this lab is to be able to identify any rock anyone ever gives you, but one thing that would be nice would be able to get a handle on whether it's igneous, metamorphic, sedimentary, and start to understand the type of things we do in order to classify rocks into different rock types. And this example here we'll go through during the prac is an example of how if you had igneous rock, how you'd work out what the name of that igneous rock is, whether it's a coarse-grained or a very fine-grained igneous rock, or whether dark minerals or light minerals are more prevalent in the rock. We have a number of questions down here that you guys will go through, and I will probably blurt out a lot of these answers as I talk my way through the rock garden. So pay attention to what I'm saying. Keep your eyes on these questions as we go. We'll be trying to identify what these different rocks are. Number of different points here that I'll talk about as we go through the rock garden itself, and I'll get you guys to fill these out. And then lastly, we'll come back into the lab and look at a rock collection in the lab, and we'll try, using our knowledge of what we learned in the rock garden, to identify whether the rock's igneous, sedimentary, metamorphic, maybe even give it a name, and then speculate on the environment in which it formed. And associated with that table we have a little cross-section of the Earth here showing a number of different rock-forming environments. There are some plate boundary volcanoes, ocean island volcanoes, a spreading ridge, the deep interior of the Earth here, sliding faults, a rift system here, mountain belts forming. And what we want you to do is take the rocks we've identified here and try and work out where in this diagram those rocks might come from. Right, without any further ado, let's talk about some different rock types.
So first I wanted to explain the difference between sedimentary rock and igneous and a metamorphic rock, because they're a little subtle sometimes in what you look for. Now, whenever you're talking to a geologist, they'll be on to you about getting in and looking at the grain, and of course when you have a bunch of students this never happens. Everyone wants to do geology from 10 meters away. But I'm going to force you to look at it because I'm going to give you little close-ups on it soon. But this is a sedimentary rock. So the first thing you might notice about it is it has sedimentary layering in it, which is really distinctive. These sediments were deposited in a quiet environment and formed up bedding layers as different layers of sediment were dropped on top over time. So that's a clear giveaway for a sedimentary pattern. The other thing you can notice here is that a sedimentary rock, of course, is made up of sediments originally. Sediments form in a near-surface environment, they're washed down from streams, they tumble down creeks, they're on beaches, getting smashed by waves. Those processes leave their dent on sedimentary grains. They tend to be rounded, the edges get chipped off, and so you end up with something that looks like sand. So sand is fairly equidimensional. You don't get kind of long, pointy bits of sand, you get little rounded bits of sand. These pieces get broken up and form these sedimentary particles like sand or mud or pebbles, and then those sediments eventually get compacted, and under pressure they start to cement themselves together, and that turns them from a sediment, which can just flow through your fingers, into a solid rock like I've got here. So sediments first off. Next up, I'm going to talk to you about igneous. Okay, this one is an igneous rock. And the way in which I can tell this distinctly as igneous rock is the shape of the crystals in it. And what you tend to find in igneous rocks, so the crystals are grown directly out of a magma, so they're quite angular. They form natural crystal shapes which have very sharp angles on them. And some of the large crystals you can see in here have very distinct sharp angles. They're quite elongate, so they're very pointy in one direction. And if you can see it really up close, all of those sharp angular crystals are actually interlocking. They form a really strong interlocking texture together, and that's a dead giveaway for an igneous rock. So in this particular case, we're looking for angular crystals that have grown directly out of a magma, and then they've grown until they're big enough that they start hitting the crystals next to them, and that gives them that interlocking crystalline texture. So that's what you look for in an igneous rock. Lastly, I wanted to show you a metamorphic rock. Now this rock, it has banding, which if you hadn't seen it before, you might be tempted to think, oh, it's a sediment, it has layers, but of course that's not sedimentary banding, this is metamorphic banding. So in a metamorphic rock, it could start life as an igneous rock, it could start life as a sediment, but under pressure and temperature, whatever the original crystals were in this rock, they've recrystallized, often into completely new minerals. Now, whilst they're under that temperature and pressure, they're being squeezed enormously like toothpaste, and often they're starting to flow, and that flow can start forming these sorts of banding in here. So this metamorphic or flow banding is actually different minerals actually forming different bands in the rock, rather than being different layers of sediment. So this is distinctly metamorphic. I can tell it's metamorphic because all the crystals are really tightly packed and angular, again like an igneous rock, but it's got this distinctly metamorphic texture. It doesn't look like nice flat sedimentary banding. It looks like something squished it like toothpaste. So, metamorphic rock. So as part of this practical, we visit a number of rocks we've actually got on display in the rock garden out here. And this, in our practical book, is actually rock number 1, which we're looking at on a beautiful sunny day, unlike a lot of the internals for whom it was absolutely pouring down. So, consider yourselves lucky. This particular rock, first thing we've got to ask ourselves is it igneous, metamorphic, or sedimentary? Now, in this particular case, I can see big angular shards jutting into other crystals here. So this tells me immediately these sharp angular grains, it's an igneous rock. So big sharp crystals forming an interlocking texture equals igneous. Now the next step in our identification is to look at it and see, well, what can we actually see? Mostly light minerals or mostly dark minerals? Now in this particular rock, it's full of this very white stuff here, which is quartz. It's also got a lot of this pinky material here. This is a form of feldspar. Together you may see them together in something like a granite benchtop in your kitchen. This is a really, really distinctive combination. For us anyway, it's a very light colored igneous rock. Now, the next part we want to identify it by looking at it is, are these crystals big or small? In this particular case, here's a big chunk of quartz. It's almost the size of my fist. When we're identifying igneous rocks, if you can see the crystals, if they're bigger than about a millimeter, they're fairly coarse. So this is very much a coarse igneous rock. It's about as coarse as you're going to find. So looking at our rock classification table here, we're at the point where for igneous rocks, we have light minerals. They're important. We've got lots of quartz and feldspar and only a few dark minerals. So we're up this end. And then we ask, is it coarse grain or fine grain? Well, this is a coarse grain igneous rock, therefore we call it a granite. Very much like your granite tabletops you might have it in your kitchen. Right, let's move on to rock 2 anyway. We'll keep recording, so we'll see how this works. Full documentary mode here. Now, with this particular rock here, if you can kind of see, it's very greenish colored. That's not the rock itself. It's actually just lichen and stuff growing on it. It's actually obscuring a little bit, but there are quite a few faces here where it's pretty well exposed still, and I can see the texture of the grains underneath. So in this particular case, I can see really large, sharp, angular grains growing together. So some of these darker materials interposed with much more whiter stuff, more feldspars, but forming this very distinct interlocking texture here. So again, that sharp, angular grains, interlocking texture tells me it's an igneous rock. Now, is it coarse grained or fine grained? Well, these grains are often the size of my fingernail, so much, much bigger than a millimeter or so. So this is still a coarse grained igneous rock. Now, the question you might ask then is it mostly light or mostly dark? Now, compared to rock 1, this is much, much darker, but on the whole, it sort of seems somewhere in between. We do have a lot of light minerals as well as the dark minerals. So, depending on exactly how you classify this, I would say that's about half-half. It's almost an intermediate composition. So in our igneous table, we have coarse grains rock, which is somewhere between maybe intermediate to dark. So if it was intermediate, I'd call this a diorite. If it had a bit more of those darker minerals, you go back to a gabbro. But for now, I'd say roughly intermediate. Let's go with diorite at this point. Now, the other rock that's right nearby here, and I'm going to destroy the focus by walking too close, but it's over here. This is a very dark rock. It's the same that you see over in these other places as well. What's distinctive about this rock immediately is the way it's actually fractured and broken apart. Only, one type of rock actually weathers like this. And if you've ever been to, say, the Giant's Causeway in Northern Ireland, you'll see this type of weathering. Now, if you did get up very, very close to this rock and peek, you can actually see in it tiny, tiny little grains, but these are sub-millimeter scale. So at this point, normally we get a magnifying glass and try and look at those grains very close up. Now, this side of it's very weathered, so as a geologist, we'd normally have a hammer at this point and would smash off a fresh bit of surface to be able to tell what those grains are. But there's a little bit exposed here, and I can see primarily dark grains here, connected with very small amounts of much lighter material in between. But by and large, the crystals in this rock are largely darker crystals, which are more rich in things like iron and magnesium, which give them this darker color. So in our igneous chart now, and again, if you did look very closely, you can see the very fine interlocking grains as well. But you'd need a hand lens minimum to be able to tell this from this rock, or even better, get a sample of the rock and we cut it up and look at it under a microscope, and then you can see those grains much better because it is a very fine grained rock. But it's a fine grained interlocking crystal rock, which makes it an igneous rock. So in our igneous classification table, again, we've got, it's a fairly dark rock, so dark minerals are important. It's very fine grained, so that would make it a basalt. And I could tell this is a basalt without even getting close to it, because this particular kind of hexagonal fracture pattern that these rocks get is very particular to basalt crystal structure. It gives you things like the hexagonal fractures you get on the Giant's Causeway, for instance. Right, let's move on now to rock 4, which is this column of rock over here. So here's rock 4. We got it from Foundation Geotechnical Core from out near Warragamba Dam. But the first thing you can see about this rock is it has really nice layers in it in different places. Very clear sedimentary layering. Now in some places, that sedimentary layering is actually cut off. It's come up like here and it's hit this boundary and then it gets cut. So the flat sedimentary layer we call bedding. And this particular structure where the sediment layers are coming off and hitting a bit where it's cut off, we call cross-bedding. But the interesting thing about that is you get cross-bedding forming in sedimentary environments where you have, for instance, sand dunes forming or waves on a beach giving you ripples. So whenever you have that kind of intertidal environment, you might form this sort of ripply structure. And then perhaps you had a winter storm come and take off a bit of sediment off the top. And then you had more layers of sediment build up in a slightly calmer environment. So you can actually tell a lot of the history of where this rock comes from that pattern of sedimentary layers. Now, most of the rock, you see it up close, is sand. It's a sandstone. So perhaps like beach environments a few 100 million years ago, the sand was being deposited. In a few places, there's some bigger grains, little pebbly sized things. So you'd essentially say this is mostly a sandstone with a few little conglomerate lenses in there. But by and large, this is very clearly a sedimentary rock, both because it's made of sand that got stuck together and it has very, very clear sedimentary layering in the rock as well. Now, the last one for this part of the rock garden is just over here. This is rock number 5. And the first thing you might think, looking at this rock, is, ooh, it's got nice layering again. It's a sediment. In this particular case, it's not sedimentary layering. And in fact, if you look closely at some of the layering, you'll see layers pinch in and pinch out. And in particular here, you can see it looks like we've formed this very light mineral layer, and it's actually been squished. It's been squished as this rock has flown like toothpaste. These layers are not sedimentary layers. This is metamorphic layering again. So in this particular case, we've got different minerals actually making up these different layers, and it was under enough heat and pressure that this entire rock was being squeezed like toothpaste again. And this gives you this very irregular layering pattern you see here. So it's a layered metamorphic rock. Now, the other interesting thing you can note about this is it has some really distinctive grains in here as well. And they're quite a deep red color. So you might be thinking, ooh, deep red grains, what does that mean? Well, it's actually a type of gemstone. Not a ruby, they tend to be more volcanic. This particular deep red gemstone is a garnet. This rock is packed full of garnets. Now, garnets generally form under middle to lower crustal conditions. So they're very indicative that a rock's been deep down in the crust where it's very hot under high pressures and then being brought back up. So they're a very typical metamorphic mineral. But this rock is absolutely popped full of them, which is an indication that it has to be a metamorphic rock. This is a metamorphic mineral and it's showing metamorphic flow banding. Okay, so this one now, we've moved out of the other rock garden up to the one near 12 Wally's Walk. And this is actually rock 6 in your Prac book now. So if you look at this particular rock, the first thing you should notice is all these layers that are all squished like this. And again, if you're paying attention before, you'd realize sediments don't get deposited like this, not in this form. These layers represent the rock being squished. They're flow banding. They're a pattern the rock's formed as it's been squished under high temperature and pressure. So this is a metamorphic texture we're seeing right here. And in fact, you can see in places, parts of these layers are actually flaked off along that banding itself. So again, minerals are lining up in different bands and giving you this very particular texture, this almost schisty texture we see in this rock. Now, it's a very, very light rock, which is the composition it's inherited from before it was formed. Often if you have something like a sandstone and you metamorphose it, it'll form a quartzite. Still quartz, nothing much has happened. If you start with a granite and you metamorphose, you'll get a slightly swished granite, so a gneiss that basically still looks a bit like granite. But in the case of a lot of sedimentary rocks, you'll actually get something quite different, particularly for the mudstones and siltstones. Those minerals aren't stable under pressure and temperature at all, and they metamorphose into quite a different suite of metamorphic minerals. So this thing started life probably as a mudstone and actually got metamorphosed under high temperature and pressure and completely realigned. We've got a lot of micas and other metamorphic minerals in here now. But the key point and the thing that defines this rock is the texture. You can see here, it's this very schisty texture. So that makes this essentially a schist. Or if you're going to be very pedantic and you remember our little metamorphic history from the lecture, it's almost a phyllite. It's almost just before you get to a schist, we've formed a phyllite texture here. So definitely a metamorphic rock. You see this flow banding. It's probably come originally from a very fine-grained sediment like a mudstone or a siltstone that's been metamorphosed and giving you this very schisty texture you see in the rock there. Right, so now if we move over in this direction here, this is not a rock on the Prac book. So if you come around here, you can see it better because we're not backlit. So this is a sandstone, and you can see the bedding surfaces in the original sandstone very well. Now, obviously, this is a statue; it didn't form here. But the point here is the bedding surfaces are now straight up and down. If you ever went out in the field and you saw a sedimentary rock and all the bedding's now vertical, you know sediments don't get deposited vertically, they get deposited horizontally. So if your sediments are now like that, the entire rock's been flipped up. And there are some famous examples of that around, probably one of the most famous being Uluru as rock in Central Australia. All the sandstone bedding that makes up Uluru is all almost vertical now, because the entire rock has been flipped up in one of the mountain building events that area's experienced. The other one, again, not a real rock, but I'm going to show you anyway, is nice rounded boulders. These are a rock we've seen, and if you look very closely, it's very fine interlocking texture we're seeing here. So angular grains, all that have grown in this interlocking texture, very distinctively igneous. Now, looking at it, it's a bit finer than some of the igneous rocks we've got, but some of the grains are almost half the size of my fingernail, so it's still a fairly coarse-grained rock. And they're quite light coloured. This is mostly white with some darker minerals scattered in. So in our igneous classification, it's a light igneous rock and fairly coarse grain, which of course makes this a granite. And you can tell that from very, very far away because granites weather very distinctively. You can see these granites that form these little round boulders. Now, granites tend to flake off around the edges as water and ice get in, and they form these really particular boulder shapes. And if you're ever driving through the countryside and you see rounded boulders out in the farmer's field, which happens out near Bathurst, or if you go north near Tenterfield, you know you're in granite country. So, granite country tends to form maybe a good Shiraz or something. If you want a good cat sav, come have a look at the next rock over here. So this particular rock, getting a little bit of foliage on it now, but it's a grey rock, which you can see immediately, and it has this kind of elephant skin texture to it, which is quite distinctive. Some of the edges of the rock are actually quite sharp. This particular rock destroys your boots if you ever have to do field work on it. Now, the moment I see a grey rock, no real identifiable bedding in there, no real identifiable crystals or anything, it's very fine grained, but if I look really close, I see some things that almost look like fossils. So I'm suspicious right now, and I'm going to ask Margari to chuck me the hydrochloric acid. This is why we wear eye protection for these things. Now, we'll try some hydrochloric acid on the rock right here. And if you can get that, you can see the rock is actually fizzing again. So the acid's reacting with the rock, it's reacting with calcium carbonate in the rock and releasing carbon dioxide. So this rock is made of calcium carbonate. It is a limestone. So this is where most of Earth's CO2 over the history of the Earth has ended up. It's been taken out of the atmosphere and bound up in this sort of rock, limestones. So this is another example of the limestone just here, but it has something really odd about it. If you look here, it looks almost organic, this particular texture we're seeing right there. And of course it is. These, if you look really closely, are actually burrow structures. So they're a trace fossil. They're not evidence of the animal itself, it's not its body parts, but these are a trace fossil that formed in this kind of limey mud back when it was a reef environment. Now, we used to think these were worm burrows in the sediment. We maybe more perhaps think these are a bit big for most worm burrows, and perhaps they're bivalves. So bivalves include things like pippies and clams and other things like that today. So you can imagine little burrowing finger clams in this limestone reef creating these burrows, moving up and down to filter feed as the tide came in, and leaving this pattern here that showed us how they lived over 300 million years ago. Now, the last one I want to show you, we're going to have to walk up. Let's walk just a little bit here. It's just down here. So, walking along, see another couple of big pores just here. Very distinctive sedimentary banding you see in there, but the real one I want to show is this rock here. Now, I'm not going to pour limestone, I'm not going to pour acid on this one. It's another limestone, but what's really amazing about it is it is absolutely chock full of fossils. So you see these amazing little sea fan patterns. These are bryozoans. You see these kind of stem-like structures just here, and there's a really nice one just there. If you see them side on, they look like stems. If you see them directly face down, they look like little circles in this rock. And these are crinoids, sea feathers, so they're filter feeders, or a type of echinoderm, like sea anemones or starfish, but they peg themselves to the ground and they filter feed things out. Not many around today, but back in the Paleozoic, these things dominated these sorts of rocks. And if you look very closely, there's a couple of shell fragments here and there, and even a little piece of coral. Now, this isn't a coral reef that we see today. This is a single horned coral. We call it Rugo's coral. So a little coral growing off by itself in an environment dominated by these other animals. So really pretty rock. If you ever let back on campus again, I do recommend coming and having a look at this yourself. All right, that's the end of the walk through the rock garden. So for this part of the prac, we have 10 rocks set up. And your goal here is to try and identify the type of rock, if it's igneous, metamorphic, sedimentary, and we'll give you some nice zoom-ins of these so you can have a look for yourself, but then also try and place the rock in the environment it's formed. And in your prac book, you have a map of the cross-section of a slice through the earth, which shows you a bunch of different rock-forming environments, and we want to fit these rocks into those environments. So your first rock, number 1 here, looks like this. So the distinctive thing about this is it has a lot of what look like pebbles in it, rounded pebbles. So this is really quite clear. It looks like something you might form today in something like a river. So if you have a mountain creek that's tumbling stones downstream, you get a lot of pebbles in those environments. If you're in a beach in, say, Britain, a lot of the beaches are formed from these, so you can get this sort of pebbly rock in those environments too. So being formed from pebbles and then stuck together, this is clearly a sedimentary rock. It's formed from sediments originally. And for this sort of pebbly texture, we call this a conglomerate. So this is a conglomerate and it's a sedimentary rock. Right, number 2. This rock, again, has this really nice sedimentary banding we see in here. And if you feel it, it feels very much like sand. So this is a sandstone. It's formed from mostly very, very small grains of quartz that have been tumbled together on a beach-like environment and then compacted to form a sandstone. So the sort of places you find sand originally might be a beach near coastal environments, on the continental shelf, in deltas, those sorts of areas as well. So sedimentary rock, very typical banding and made up originally of sand. So that makes it a sandstone. Okay, moving on to number 3, which is this greeny looking rock here. Now, if you could feel it, it actually has a distinctive feel to it, this rock. It almost feels a bit soapy or something. Some people actually call varieties of this soapstone because they have minerals in them like talc and things that can actually make them quite slippery. Now this particular rock, if you look closely, it's got these very fine layers that if I felt like destroying it, I can actually flake off. So it's formed very fine banding along here. That's not sedimentary though. Very platy, very silvery, which is a lot of the mica minerals in this rock, and forming this really flaky sort of pattern. So this particular rock is metamorphic. That flaky, schisty pattern is a very typical metamorphic texture. And that makes this rock what we call a schist, that particular texture it's got to it, which is the pun of nearly all geology undergraduate jokes. So this is a schist, this is a metamorphic rock that's been under fairly extreme pressure and temperature conditions, maybe in the core of a mountain belt. It may have originally been something like a sediment that's been squished and all the minerals in it have been metamorphosed into new metamorphic minerals. Now, if we took something like this and went even to more extreme temperatures and pressures, we might end up with a metamorphic rock like this. So again, it has banding in this rock, but it's not sedimentary banding, it's metamorphic banding. Different minerals actually make up these different layers, and they're not nice flat beds. They pinch in, they push out. The entire layer has been squished and squeezed like toothpaste. It's a very crystalline rock. There's very definite crystals all interlocking in there, but these are grown in a metamorphic environment. This is about as extreme as a metamorphic rock gets before it starts to melt, and so this is called a gneiss. Right, rock number 5 I've got here starts to look very bubbly. So there's lots of air bubbles in this rock. It's very sharp. If I look at the bottom, there's lots of crystals in here too of a greeny material, which we'll talk about later on. Now, this you may have seen, rock with lots of air bubbles in it. We're familiar with it in New South Wales. It forms something called pumice, which is often washed up on New South Wales beaches, often shortly after Tonga erupts out in the Pacific Ocean. We get a lot of pumice coming over. This is darker than the pumice we generally get from Tonga though, but it is volcanic like this. So this is a volcanic rock in which air bubbles have formed as it's erupted. So it's very sharp, it's a dark volcanic rock. If I'm looking at it, I can't see, apart from some of these big crystals, but I can't see any crystals in the ground mass itself. So the basic ground mass is a very dark volcanic rock, which makes it a basalt. Now, the complication with this is that if you look though, the ground mass is very fine, but it has some big crystals in it. And they're actually crystals that grew deep underground originally, whilst there was the magma chamber underneath the volcano. The crystals started to grow, and then they get dragged up by the lava from deeper down and erupt with it. So some of these crystals formed in the magma chamber, some of them have probably come from even deeper down, scavenged from the mantle itself. So as a result, these sorts of rock can have some big crystals in them, but the key here is we're calling it after what the ground mass looks like, which is very, very fine. So it's a fine-grained, dark volcanic rock, which makes it a basalt, just with some extra crystals involved. So the thing with the bubbly basalt here, or a vesicular basalt as we call it, because it's got vesicles in it, is that, well, you don't get the gases you need coming out of a magma if it's under high pressure. Generally, in order to start forming bubbles in a magma, so getting CO2 and water bubbles forming in a magma, you've got to actually let the magma come up to low pressures, and then those bubbles start coming out. Usually the top 2 kilometers or so, you start forming bubbles. Generally, if we see something this bubbly, we know it's erupted underneath air. So it's actually been what we call a subaerial eruption. So in places like Hawaii, you might see stuff like this. If you erupt basalt under a lot of pressure, say at the bottom of the ocean, at a mid-ocean ridge spreading center, you're not likely to see this amount of bubbles, which should help you identify the environment that this basalt might have come from. Right, leave that there. We'll move on to rock number 6, which is this one here. So I'm looking at it. The first thing I see immediately is it's not quite as dark as the basalt. It's not very light. It's somewhere in the middle. It's a grey colour, kind of black and white minerals speckled throughout, very distinguished rock. But within it, it has some very big, sharp grains as well. Now, the ground mass here is very fine, but there are lots of crystals I can see in there interlocking together. So this makes it a volcanic rock as well. They're very much volcanic crystals that are grown in a magma chamber. Now, as to exactly what we call it, some of those crystals, again, are quite big, and they probably grew in the magma chamber underground. But the ground mass here, the grey material, is actually very, very fine. And so we're going to call the rock after the ground mass, which was the last thing that happened to it. And so although it's grown crystals deeper down, as that magma's come up, it's erupted. So it's actually an eruptive rock, and it's got a very fine ground mass. So I'm looking at this thinking, it's got about half dark crystals, half light crystals. It's an intermediate rock. It's volcanic, definitely, because of these big angular crystals, and the ground mass itself is quite fine. So a fine-grained volcanic rock of intermediate composition, that makes this an andesite. An andesite is, of course, named after the Andes mountain range, where you find a lot of this stuff erupting in that sort of convergent margin setting. Right. Moving on to rock 7, this is a fairly dull, innocuous looking a little affair. It's this little grey rock, but if I look closely within it, I immediately see very, very fine sedimentary layering in this rock. So this straight away is very obviously a sediment, and in fact, the particles in here are almost too small to see, but I can tell from its texture, they're very, very fine-grained particles, down around light or sill size. Now there are ways of being able to tell the difference between a mudstone and a siltstone in the field. One such way is to lick it, which is how I was taught. If it tastes gritty, then it's a siltstone. I'm not going to lick this rock for you. This is a clear health risk at the moment. So it's been in a lot of hands and not been sanitized. There are a lot of problems licking rocks in the field. When I was taught this by a geologist, he licked a rock in the field and go, "Yeah, lick this, Craig." And I looked where it came. Not only had he just licked it, but it was sitting right next to a cow pat in the field. So I kind of moved away from licking rocks as an identification there. But if you needed to, one can identify the style of sediment it actually is by licking it. But this, anyway, it's a very fine-grained, muddy sediment. We're going to call it a mudstone. Okay, moving on now to rock 8 here. Now, as opposed to the mudstone, which I should mention forms in a nice, quiet sedimentary environment, somewhere there's not a lot of energy, so a mudstone would typically be a lake or the deep ocean where the currents are very, very slow. This comes from almost the exact opposite. Now, the rock here is not the black volcanic rock around it. The rock I'm interested in here is this green material in here. So many people got that this kind of olive greeny material is actually a mineral called olivine. So there's a lot of this light green stuff is made up of olivine. Now, olivine, of course, is what most of the mantle is made of, and this rock actually comes from the mantle. It's something which in English you translate it as outside rock, and it's Latin, it's xenolith. So this is a xenolith. It's actually come from all the way deep in the Earth's interior in the mantle and being brought up by an eruptive event, in this case a basalt volcano. Now, it's not only made up of olivine, it's got little flecks of darker green and blacky minerals in there as well. So they're pyroxenes and other stuff. But together they make up a rock type which we call peridotite. But generally to find peridotite, you've got to be underneath the crust. It's actually come from somewhere very deep down in the interior of the Earth, underneath the crust itself. Right, rock number 9 now, very black. It's a very rock and roll rock. If you look at it again, I can see some big crystals in here. Some of them are very angular. It's a very dense, tough rock as well. So immediately I see these big sharp crystals that have been embedded in it. I know it's volcanic. Okay, even though I can't see them all interlocking because a lot of the ground mass is very fine, those big sharp crystals tell me it's a volcanic rock, if nothing else. Now, looking at the ground mass itself here, even though it's got some big crystals in, again, they've probably come from a magma chamber deeper down and been brought up with the magma. It's erupted as a lava and crystallized to form a very fine ground mass around it. So, it's a volcanic rock, it's very dark, the dark minerals are prevalent, and it's very fine-grained. So that makes it a basalt in a volcanic classification scheme. Right, the other thing to note here is that as opposed to the other basalt we've already had, this basalt has no bubbles in it. So plausibly it's erupted under perhaps higher pressure conditions. If you were to erupt a basalt, for instance, at a mid-ocean ridge under 2.5 kilometers of water, that's the sort of pressure you need to inhibit bubble growth, and you wouldn't get bubbles in a rock, for instance, that would form at a mid-ocean ridge. Right, and the last but not least one is this guy here. Now, straight away I look at this and I can see fossils in this rock. There's a shell. It's actually got a shell fragment right there of a little bivalve. It's got a little stem here from a crinoid, so a sea feather. The entire rock, if I turn it on its side, is all shells the whole way through. So this is made from living organisms. But it is classed as a sedimentary rock. It's a sediment of the shells of once living organisms. So I know what those shells are made of. They're made of calcium carbonate. A lot of those CO2 ended up in rocks like this, which makes this a limestone. Now this is a very obvious limestone because it's full of fossils. Not all limestones are as obvious. So I'll show you a little test, just in case you're ever wondering if a rock is a limestone or not, how you could potentially tell. Okay, so this is our little limestone rock just here, and just to show you how you'd normally figure out if it is a limestone or not, I've got a 1 molar hydrochloric acid solution here, and I'm going to put some onto the limestone, and what you can immediately see there is the limestone is fizzing. It's reacting with the acid. So being a limestone, it's a calcium carbonate, and it reacts with the hydrochloric acid to release CO2. So those little bubbles you're seeing are CO2 being released into the atmosphere. So single-handedly just contributed to global warming right there.